Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is video 41. We're in lecture 19, part B, and we're talking about the difference between two means and hypothesis tests. There's a special case where they're equal, mu1 equals mu2, and if I subtract mu2 from both sides, I'm left with this is equal to 0. So this is a special case. We're going to learn the general case so that we can set this difference equal to whatever value we want and then test whether it's that much, okay? Or more or less or at least that much, okay? So first thing I want to remind us is when n is less than 30, the data has to be normally distributed in order for us to use the methods in this chapter and in the last chapter for confidence intervals. If the data is not normally distributed, then we'd have to use some other method, most likely a non-parametric method for hypothesis testing, okay? Now, why would we care whether we used a parametric, which is what this is, or a non-parametric method? The answer is in the power of the test. Usually, non-parametric tests have less power than these parametric tests. But again, if you don't have normally distributed data, then this test is no good. All right. So let's summarize what we did in the last video. We talked about paired data. And for the most part, these are dependent, I'll say samples, but populations as well. Okay? So they're dependent because we're taking the same person and taking two different measurements, and so those two measurements are not independent of each other because they're on the same subject. Okay? Now, for n is less than 30, where we don't know sigma, then we use t, okay? And it has a t distribution with n minus 1 degrees of freedom. When we have a sample of at least 30, then we can use z, the standard normal, by the central limit theorem. Okay? Now, when we do know sigma, then we can use z. But again, if n is less than 30, then the data has to be normally distributed, okay? Now we're going to talk about comparing two independent means, okay? So I say that the two populations are independent here, but that's not technically required. The two samples have to be independent. If the two samples are independent, then we're fine. You say, well, if the populations are dependent, how can we create independent samples from each of these populations? Well, usually populations are dependent because they have some of the same members. So as long as we don't choose the same subjects for the two, if that's the reason they're dependent, then as long as we don't choose the same subjects, then we're okay. For instance, we might have family members. So our populations might include family members who are definitely, because of genetics, they're definitely related or dependent upon each other. So the only way that we could choose an independent sample from those two dependent populations is to make sure that if, let's say we chose a husband and wife, they just can't be, or husband and wife if it's married couples, families. So we choose a parent and choose a child. The only way to make those independent is that the parents and the child are not the same. So if we choose a parent from a family, then we eliminate their children from the other sample. So we have to make them independent in order for us to use these tests. If the samples are independent, then the means are independent and the standard deviations or variances are independent of each other. But that's only when the samples are independent. Test statistics. If either N1 or N2 or both are less than 30, then we have to use T. And here we're not assuming that we have a common variance. So if we don't have a common variance, then we have to use Welch's t-test. Because we don't have a common variance, instead of trying to use a pooled variance, we use S1 squared and S2 squared in the equation. But the degrees of freedom have to be calculated with this not so lovely formula. Now, when we have at least one of the variances are unknown, but we can assume that they're in, so if we don't know the variances, but we can assume that they're equal, then we use this formula where we use the pooled variance. So what we do is we pull out these sample variances and estimate this pooled sample, the overall variance. And we do that by using what we call a weighted mean of the variances. So n1 minus 1 over times s1 squared, n2 minus 1 times s2 squared, add those up, and then divide by n1 minus 1 plus n2 minus 1, which becomes n1 plus n2 minus 2. In this equation, the degrees of freedom are a lot easier to calculate. It's just n1 plus n2 minus 2. Okay? And then if we have both n1 and n2 are at least 30, and it doesn't matter if sigma 1 or sigma 2 is known or unknown, we can use z, okay, by the central limit theorem. And this is where we have no assumption about equal or common variances. All right? And we don't have to worry about degrees of freedom because it's a z. So if we know sigma 1 and sigma 2, then we can use this version of z, and it's the same, except instead of S1 and S2, we have sigma 1 and sigma 2. This is rarely used because we rarely know the population standard deviations without knowing the population means. Okay? It's rare. So those are our 4 different test statistics that we can use in this section. I hope you'll write them down and put them on a formula sheet. Same way I hope you wrote down the confidence intervals and tests for one mean so that you can find these easily. Okay. So let's do an example. We have a furniture manufacturer, and this furniture manufacturer wants to show that adhesive 1 is superior to adhesive 2. I don't know why I said 20. In terms of the mean force required to pull apart glued pieces. All right, so if an adhesive is superior, that means its adhesive strength is greater than the other. So we could write this as mu1 is greater than mu2. Okay? Or we can rearrange this so that we have mu1 minus mu2 is greater than 0 if we subtract mu2 from both sides. All right, so let's look at the sample data. So we have adhesive 1, we have a sample size of 24. Adhesive 2, we have a sample size of 24. The mean force required for adhesive 1 is 1216, and for adhesive 2 is 1118. Here are their sample variances. This is n sub I, this is mu sub I, this is s sub I squared, because it's variance. So A, assuming equal population variances, test at alpha equals 0.05, the appropriate hypothesis. Okay, so hypothesis statement, we're going to write them as mu1 minus mu2. If they're the same, equal 0, then mu1, or adhesive 1 is not superior to adhesive 2. If adhesive 1 is superior to adhesive 2, then its mean force is greater than that of mu2, and so this will be 0, as we showed right here. And we're saying tested at alpha equals 0.05. So the test statistic that we're going to use is the one where we assume common variances, so we have to use the pooled sample variance, or sample standard deviation here. And here's our formula for the S sub p squared. And I wanted to show you that if n1 and n2 are equal, and we'll just call them n, then we have, this just becomes n, this just becomes n, so then we have n minus 1, n minus 1. So we have that in both terms, we can factor it out, n minus 1. And then n plus n is 2n, and I can factor out the 2 there, and I'm left with 2 times n minus 1. There's no addition. If there's addition up here, we can't do this, but there's no addition. We have n minus 1 times s times something in parentheses, and then we have n minus 1 down here. We can cancel those out, okay? So we're left with just S1 plus S1 squared plus S2 squared over 2. This is only when N1 is equal to N2. And we get 30,054. So that's my sample variance, my pooled sample variance. So I'm going to put this down here, square root of 30,054. Okay. Now I need the square root of 1 over 24 plus 1 over 24. That's going to be 2 over 24, or 1 over 12. Now I need x1, x bar 1, which is 1216 minus 1118 minus mu1 minus mu2 is 0. And this gives me 98 divided by, and so I've got, so I can do 30,000. This will be 2 over 12 if I add these up. So 30,054 over, it'll be 1 over 12. 2 over 24 equals 1 over 12. So I can say 12 and then square root. Make sure you keep that under the square root. So I've got 98 divided by second square root, 30054 divided by 12, close that parentheses, and I get 1.9582, etc. For a t-table, this is t observed. I need 3 decimal places. My table has 3 decimal places, so 1.958. Now my critical region is we reject H naught if this is true. So to do this, I need my degrees of freedom. That's going to be N1 plus N2 minus 2. That's 24 plus 24 is 48 minus 2 is 46. So I need to use 30 for the degrees of freedom because my table only goes to 30. So for this table was set up because they assumed that you would go to the Z table if you have n greater than 30. But this is degrees of freedom greater than 30. That's not true. They have to be greater than 60 for two means, right? For this, so we're going to use this line here, and it would also include this one, depending. Okay, so I'm using alpha equals 0.05, and so I need to look back here, and what we were doing is we want T naught. So T naught, since this is a one-sided test, T naught equals T sub alpha equals T sub 0.05 and 46. So we're going to use 30, which will be safer because it'll be a bigger number. So it'll be more difficult to reject. So we've got T 0.05, 46, and that's 0.05. So we'll look at 0.05 here and come down to 30, and that's going to be 1.697, which is bigger than 1.645, which is what we'd use if we have Z. So 1.697, 1.697, and so we want to know if 1.958 is greater than 1.697. It is, so since it is true, we do reject H naught. So since we did reject H naught, there does exist sufficient evidence to support the claim that the mean force required to pull apart glued pieces is greater for adhesive 1 than the force required for adhesive 2 at a 95% confidence level using N1 equals N2 equals 24 glued pieces. We want to find the p-value of this. So T observed is 1.958. So we need to use, for the 30 degrees of freedom, we want to find 1.958 is between these two values, 1.697 and 2.042. So that's going to be, since it's a one-tailed test, it's going to be between 0.025 and 0.050. That's our p-value. That's the best we can do. Okay? It's between these two numbers for degrees of freedom equals 30. And so we have between 0.025 and 0.050, which agrees with our decision to reject the null for alpha equals 0.05. See, we did reject the null here using the critical value method, and we also, because this p-value it says right here is less than 0.05, which is alpha. This is alpha in this case. So if p-value is less than alpha, we reject the null. It is less than alpha, so we are going to reject the null. Now, example 2 is going to be the same as example 1, except we're not assuming that the variances are equal. They're unknown and we don't know. So this is Welch's t-test, and since n1 or n2 is less than 30, it's Welch's t-test. Okay? So we're going to calculate nu. By the way, this is a Greek letter nu. And I plug in the values, so I'll let you calculate these. I didn't want to take time up to calculate this while we were on the video. But make sure that you get the same answer. Okay, so you plug in the variance over 24. These are the same denominator, right? So, and then we have the same denominator here. And so we can add these values here and then this, and we square both top and bottom. Guess what's going to happen? These are going to cancel out. They're squared down here as well. Okay, so they're going to end up canceled out, and so we end up with 44.55, and we'll round down to 44. So we always round down the degrees of freedom, and the closest is 30 in our table. H naught, mu1 minus mu2 is equal to 0 versus mu1 minus mu2 greater than 0. Remember, we're trying to show that mu1, or that adhesive 1 is superior to adhesive 2, or that the mean of adhesive 1 is greater than the mean of adhesive 2. Our test statistic is now, instead of using the pooled variance, we'll just use the sample variances in the formula because we're not assuming that they're different. And so we plug in to our equation, we end up with the exact same value, y. We end up with the exact same value for both test statistics because n1 is equal to n2. That's the only reason. If they're not equal, you won't end up with the same value. Okay. So our critical region is reject H naught if T observed is greater than T naught. Okay. So here, our degrees of freedom, is supposed to be 46. Here it was 44. Oh, wait, no, yeah, that's right. So before it was 46 in the previous example, 46 degrees of freedom. And in this one, it's going to be 44 degrees of freedom. So it would be a different, if we were using a computer, there would be a different critical value. But because our table only goes to 30, we'll end up with the same critical value. T of 0.05 at 30 is 1.697. We have exactly the same critical value. So this is a true statement. So we do reject H naught, and there does exist sufficient evidence to support the claim. Same exact. Now the p-value here is going to be the same because we have 1.98, and we ended up looking at the same degrees of freedom, which was 30. Okay, so so we're between 2.042 and 1.697. Okay. And so again, we have a p-value here. And so if we were using the p-value method, we would still reject H naught because p-value less than alpha. And this is 0.05. And it says right here that p is less than 0.05. So reject H naught. So I've done some calculations here for you. I'll let you do this. But when we have N1 equals N2 equals N, then the degrees of freedom, the nu, reduces to this. So I just wanted to show you these easier formulas. And then the same thing, T observed and with common variances, you're going to see that they're the same if when N1 equals N2. And so I gave you some easier formulas here to use when N1 is equal to N2. But be careful, it only works when the sample sizes are the same, okay? But these formulas are a lot easier to calculate. If you have questions, come to virtual office hours. If you need help before office hours, then by all means email me, but send me a picture of the problem because I won't have it available, and a picture of your work so far so I can see how you're approaching it, and I'll be happy to help you. Please take care of yourself, stay safe, because we hope to see you here next time.